All right, today we're going to start with our equilibrium problem. So they give you an equation on the top. You got carbon solid plus CO2 gas gives you 2 CO gas. So it goes from carbon and carbon dioxide to carbon monoxide. It says solid carbon and carbon dioxide gas at 1160 Kelvin were placed in a rigid 2-liter container, and the reaction represented above occurred. As the reaction proceeded, the total pressure in the container was monitored. When equilibrium was reached, there was still some CO remaining. That might be important. Results are recorded in the table below. A couple things that jump out to me right away. This is the temperature. This is the volume. Okay? Then, on the table itself, it says total hours. So it kind of sounds like kinetics. And then, or sorry, time in hours, and then total pressure. So sorry, time, hours, and then there's your total pressure of gases. So let's jump into it. Letter A. Write the expression for the equilibrium constant Kp for the reaction. So I want the equilibrium constant Kp. So reminder, equilibrium expressions are generic. You can only include gases in aqueous solutions. So if you look up top, this is a solid. You do not want that. You don't want that. Okay? So, you need to do a Kp. Reminder, this is wrong. If you do brackets, that's Kc. You do not want brackets. You want a pressure with a subscript. Pressure CO, pressure CO2. What's missing, you have to make sure that you do your coefficients. So because there's a 2 right here, you need to have a 2 right here. Parenthesis or not, you don't need that necessarily. Okay? But if you do, that's great. All right. Next, letter B. It says calculate the number of moles of CO2 initially placed in the container. Okay, the number of moles initially placed, So this is N. So you got to start asking yourself, this is about gases. You have moles, okay? You have N right here. You have T, and you have V. So what's missing? You're missing P. This is screaming ideal gas law. So this is screaming this. But you need P. So initial CO2 initially placed in the container. If you check it out, look up top. CO2 is what you start with. So at time 0, that would only be of CO2. So that is my pressure. So now I can move forward with that. My volume, 2 liters. My R value, always the same. And my temp. Already in Kelvin for me. How nice. I do my calculation. And that's how many moles I have. And I'm sorry, if you need to know the points, this was worth 1 point right here. And then PV equals nRT is always 1 point for the setup, 1 point for the answer. Okay? All right, letter C. This is broken up into 2. So letter CI. I like I's and double I's because what it does is it gives you little smaller problems that you can easily figure out as you go. Okay, so it says for the reaction mixture at equilibrium at 1160 Kelvin, so same conditions, the partial pressure of CO2 is 1.63 atm. This is at equilibrium. Calculate the partial pressure of CO. Okay, well, what's happening here? What you need to do is think about what is occurring within the entire problem. What is occurring is you have 2 gases. You have CO2 and you have CO. At equilibrium, what does that mean? If you take a look right here, this is very typical of a problem. After a certain amount of time, after 8 hours, I have a certain amount of pressure, and after 10 hours, I have the same amount of pressure. So this must be, oops, sorry. This must be at equilibrium. It must be. So that's my total pressure. So this is what you should be thinking, even if you don't write this, is that pressure total equals pressure of my CO plus pressure of my CO2. That's what I'm having occur. So I have 8.37. That's my total. And then I was told that my partial pressure is 1.63. And sorry, that's of CO2. So pressure of CO would be that. It says 1 point earned with correct method. So if you don't show your work in some way, you don't get the points. So that is worth 1 point, but you had to show some understanding. When it says calculate, you cannot just have an answer with your calculator. Double I. It says the value of the equilibrium constant Kp. Very important to keep straight is that when you are asked to solve a K, that means that everything must be known within my K. So everything must be known specifically in my K. So I'm going to plug this in. Kp equals now, and I have partial pressure of CO over CO2. So I have 6.74. Make sure you square it, because it still fits into the expression, 1.63. And what you get is 27.9. Amazingly enough, 1 point is earned that you put the numbers in the right spot. 1 point is earned for the final answer. If you accidentally put in the carbon from the beginning that it was a solid, you might have been able to rescue yourself because you noticed in double I that you weren't given anything about carbon, so maybe you'd realize that you should have crossed that out. Okay? All right. Let's take a look at D. If a suitable solid catalyst were placed in the reaction vessel, would the final pressure of the gases at equilibrium be greater than, less than, or equal to the final total pressure of the gases at equilibrium without the catalyst? Justify your answer. All right, I'm not going to write a lot about this right now, but I will get you started. Well, you need to ask yourself, what does a catalyst do? A catalyst speeds it up. All right, well, a catalyst can confuse a lot of people and say, well, if it's going to speed it up, then it's going to make more products and thus bigger pressure. It's going to make products faster, but equilibrium is reached regardless. So all we're going to do is get there faster. So it will be equal. Okay? The pressure at equilibrium will be the same with or without a catalyst. The catalyst simply allows equilibrium to be reached okay. After all that said and done, though, that's only worth a point. Okay, so be careful. The only thing that can change your K value is temperature. And last but not least, it says, predict whether the partial pressures of CO2 will increase, decrease, or remain the same as the system approaches equilibrium. Oh, I'm sorry. I didn't read the situation. It says, in another experiment involving the same reaction, a rigid 2-liter container containing 10 grams of solid plus the gases, each at 2 atm. Okay. The minute you're given new amounts, you got to ask yourself, is that in equilibrium? Well, if it's at equilibrium, what you have to ask yourself is, what is the Q? Okay? So they said that they were both at 2 atm. So all I do is I plug in my pressures in the same way as Kp. When I do that, I get 2.00. What do you do with a Q? You compare it to a K. So the easiest way I can write this is that's K and that's Q. So what you need to ask yourself, you got to be careful. This is 2 steps. What does this do, and then how does it affect my question? Because Q is less than K, it's going to drive it to the right. So if you look at the equation is C plus CO2 makes CO. So the question is, what happens to CO2? Well, if it's driving it to the right, that means this is going to decrease. So you can say it in a bunch of ways. You get 1 point for just calculating 2, and then 1 point for justifying that it decreases. I'd say something to the effect of, because we are not at equilibrium, it will go towards the K, the equilibrium constant, towards the K, which causes the reaction to drive to the right, which produces less or fewer CO2 particles. And that's that problem. So that is chapter 13. That's equilibrium. All right, let's take a look at chapter 10. This is liquids and solids. This is a really old problem, but it's a really good one. So what this is saying is, it says, account for each of the following observations about pairs of substances. In your answers, use appropriate principles of chemical bonding and or intermolecular forces. In each part, your answer must include references to both substances. So let me lay out each one. So it gives you NH3 and CH4. And it says that this has a higher melting point than that. So they did you a favor. They told you this is higher. Sometimes it's hard to interpret that with negatives. So your job is to interpret what type of intermolecular force or bond there is, and then why. It's not your job to disagree. So you have to take this instance, look at it, and then you need to justify why using information, even if it looks like it's opposite or contradictory to what you believe. So what you should do is first state what each have, okay? So if you look at this, by the way, just so you understand, this is what this one would look like, and this is what this one would look like, right? So what I would say is something like NH3 has H bonding, while CH4 has London forces. Okay, let's make sure we understand what melting point means. Melting point is when you are melting it from a solid to a liquid. You're going in a phase change. So what you're doing is you're overcoming these forces. You need energy to overcome these forces. So it would take more energy to overcome a stronger force. Okay, so what you just have to establish is which one's the strongest one. So NH3 has a higher melting point due to the fact that H bonds require more energy to overcome the forces than weak LD forces. Done. 2 points. 1 for identifying each bond, 1 for the explanation. Letter B. Gives you 2 more situations. It says at room temp, this is a gas, and this is a liquid. Okay? I'm not going to write every single explanation for you here at this point. You need to kind of formulate it based on what I had first. So what you need to look for on this one is the fact that the difference is the gas and the liquid. This is the difference. So if you recognize this, and the drawings aren't good enough to help explain, this is more for you, is that these are both LDs. So let's ask ourselves, what does it mean to be a gas versus a liquid? If you are a liquid, you are more attracted to each other. There's more attraction. What does that mean? Stronger IMFs. Well, wait a minute, they're both London. So you got to recall the rules about London. C6H14 is a larger molecule with a larger electron cloud. the LDs forces are stronger in larger clouds. Stronger with larger electron clouds. You could continue on and say it causes more induced dipoles and things like that. Again, if you have time, you should feel like you should add that kinds of materials. That'd be great. So that is that one. Letter C. Talks about melting points again. Okay, that's not even close. Look how much higher the silicone melting point is than the chlorine. So there's something extreme going on here. And if you can remember it, that's great. If not, this is going to be kind of hard for you. These are LDs because they're nonpolar, and silicone is a network solid. So you need to come up with that. So please formulate it in the same way. I'd say silicone has a network solid while Cl2 has London dispersion forces. To overcome a covalent bond, remember these are covalent. That's important. They're all covalent bonds. To overcome a covalent bond, you require a lot more energy than a London dispersion force. So that would be the route that I would go for that one. And then finally, very important problem. You have two salts. Again, they're giving you all the information already. So this is a much higher melting point than that one. All right, these are both salts, and this was on our practice test. Salts come together, they make a crystal lattice. So it's actually lattice energy. It has to deal with Coulomb's law. And simply put, it deals with their charge versus their size. So you can just do the math. The higher the larger the top number, or the smaller the bottom number, the greater the lattice energy. That means the more energy it takes to break these apart, to separate them. So simply put, these have a plus and minus 2 charge. This is a plus or minus 1 charge because they're basically the same size. So what I would do, again, I'm sorry, I'm not going to give you the entire explanation on this, is I would explain and go into depth about the fact that these are plus and minus 2 charges, while Na and NaF only has a plus and minus 1 charge. And the larger the charge, the greater the amount of energy needed to remove or to separate or to phase change or to overcome. Reminder, temperature is a measure of energy. So the more energy needed to overcome these, that is a sign from temperature. Okay. Lastly, chapter 11. We didn't really do this much in class, the actual chapter, but this chapter really kind of bleeds into other things. So we just have part of the problem to do, and we're going to go through it right now. So on your sheet itself, you have these structures. I don't have them on here, and I apologize, but it's glucose versus cyclohexane. And you look at both. So A, it says, identify the type or types of intermolecular attractive forces. Now, here's a little clue. If you have hydrogen bonding, then you probably also have dipole-dipole in London. If you have dipole-dipole, you also have London. If you have London, that's all you have. So it kind of is a hierarchy. Usually you can get away with just naming the top strongest IMF. So if you take a look at the glucose, you have several, I count 4, 5, hydroxyl groups. And OH creates hydrogen bonding. So for the glucose, I have hydrogen bonding for sure. If you feel like you need to name the other ones, it does have dipole-dipole with that oxygen bond, and it's not symmetrical, and everything has London. Okay? For the pure cyclohexane, it is completely nonpolar. It is completely symmetrical. So when things are nonpolar, it's simply London. And that's all it is. Letter B. Glucose is soluble in water, but cyclohexane is not soluble in water. Explain. Okay, you can talk a lot about a lot of things. But here is something you just want to focus on. Water is like this. And I have this H bond. Okay? So, to be honest, I would love us to try to go along these lines, is that when hydrogen bonds are made, one breaks off and another one is created. Glucose is soluble in water, but cyclohexane is not. The glucose, talk about the substance, the solute, and the solvent. So I say glucose has H bonds, which are able to create new H bonds with H2O. Cyclohexane cannot make these bonds, and thus is not attracted to H2O. Another route you could definitely go on is saying that water is polar, glucose is polar, cyclohexane is nonpolar, and then discuss how polar molecules are attracted to polar molecules because of the attractive forces that are inherent in them, while cyclohexane has no polarities or charges or partial charges, so they will not be attracted to those charges. You can talk about one or the other. Okay? Letter C. It says, consider the two processes below. I. For each of the two processes, identify the type of intermolecular or intramolecular attractive forces that must be overcome for the process to occur. I'm assuming you need to be specific. You cannot just say, oh, that's an inter and this is an intra. It says what type of inter and what type of intra. So process number one. This is a phase change. You're going from a liquid to a gas. You're still looking at it as water. So you're overcoming IMF. So this is an intermolecular and specifically H bonding or H bonds, however you want to refer to it. Process number two, you are ripping H2O apart into its elements. So this is an intramolecular, and specifically, there's only two kinds. As far as you're concerned, there's ionic compounds or there's covalent compounds. Those are covalent bonds. So if you just write covalent bonds, you'll be good to go. So that's how that one works. And lastly, double I. An agree or disagree statement. As I've said, please be careful. Indicate whether you agree or disagree with the statement in the box below. Support your answer with a short explanation. When water boils, H2O molecules break apart to form hydrogen molecules and oxygen molecules. So they say when water boils, molecules break apart to form hydrogen molecules and oxygen molecules. When water boils, if you look up, it makes process number one. What they're trying to say is when water boils, it does this. It goes from that to that. So I totally disagree. When water boils, you are breaking apart intermolecular forces, H bonds, not intra, which would be covalent. So that's solutions, and we'll continue our review as we go.